In this lesson, we are going to discuss the generalized mathematical induction. Oftentimes, we wish to prove a statement of this form. P of n is true for all integers n greater than or equal to a, where a is a fixed integer. In order to prove statements such as this, we use the generalized mathematical induction. We have a fixed integer m and we have an open sentence with domain equal to the set of all integers greater than or equal to this fixed integer. Suppose that these two conditions are true. P of m is true, and for all integer k greater than or equal to m, if P of k is true, then P of k plus 1 is also true. If these two are true, then for all n greater than or equal to m, P of n is true. Take note that the only difference of the generalized mathematical induction is that your base case is no longer equal to 1. In this case, you can start at a particular value m. If it so happens that P of m is true, and if you get a k greater than or equal to m, and if the implication P of k implies P of k plus 1 is true for all k greater than or equal to m. So we can now use that at our base case. Since P of m is true, the second condition says that P of m plus 1 is also true, and so on, and so on. So that means for all of this P of n's are true, where n starts at m. Take note that PMI is just the generalized mathematical induction with the fixed integer equal to 1. Here is our first example. For each integer n greater than or equal to 4, we have to show that n factorial is greater than 2n. So for our proof, just like with PMI, you have to clearly identify what your P of n is. In this case, your P of n is this statement. N factorial is greater than 2 raised to the n. We start with our base case. What is our base case? N is equal to 4. For our base case, we write when n is equal to 4, 4 factorial is equal to 24, which is greater than 16, and your 16 is 2 raised to the 4. That takes care of the base case. For the inductive step, we start with let k be greater than or equal to 4, and our inductive hypothesis is that k factorial is greater than 2 to the k. We want to show that P of k plus 1 is true. That is, k plus 1 factorial is greater than 2 raised to k plus 1. In order to prove this inequality, we start with the left-hand side. We want to make use of our inductive hypothesis, k factorial greater than 2 to the k. In order to have an expression involving k factorial, we will write k plus 1 factorial as k plus 1 times k factorial. And therefore, this is greater than k plus 1 times 2 to the k. Let us have some scratch work here. We already have k plus 1 times 2 to the k, and we want to end up with 2 to the k plus 1, this one. We write 2 to the k plus 1 as 2 times 2 to the k. So therefore, all we have to do is to show that k plus 1 is greater than 2. Is it true that k plus 1 is greater than 2? Yes, because in particular, your k plus 1 is greater than or equal to 5. Your k starts at 4. So therefore, we will proceed using this argument. This is where we use this fact that k is greater than 4. Since k is greater than 4, this is now greater than 2 times 2 to the k, which is now equal to your 2 to the k plus 1. Therefore, we have just shown that n factorial is greater than 2 to the n for each integer n greater than or equal to 4. For our next example, we will show that for all integer n greater than or equal to 5, we have 2 to the n is greater than n squared. First, our P of n is this statement, 2 to the n is greater than n squared. We will start with our base case. When n is equal to 5, 2 to the 5th, which is equal to 32, is greater than 25, and your 25 is 5 squared. We now proceed with our inductive step. Let k be an integer which is greater than or equal to 5, and suppose that 2 to the k is greater than k squared. We want to show that 2 to the k plus 1 is greater than quantity k plus 1 squared. In order to prove this, we will start with the left-hand side and show that it is greater than the right-hand side. First, we write 2 raised to k plus 1 as 2 times 2 to the k so that we may use our inductive hypothesis here. This is 2 times k squared. Now, remember that we want to end up with k plus 1 squared, which is equal to k squared plus 2k plus 1. I already have a k squared here, so I will write my 2k squared as k squared plus k squared. So what we want to show is that k squared is greater than 2k plus 1. How do we go from here to here? What we need to do is to sort of peel this term. What do I mean by peel it? Your k squared is equal to k squared plus k times k. But what is our assumption about k? Your k is greater than or equal to 5. So therefore, this k squared over here is greater than or equal to 5k. So this is greater than k squared plus 5k. And then I want to have a 2k. So we will now express our 5k as 2k plus 3k. And of course, your 3k will now be greater than 1. In particular, your 3k is greater than or equal to 15. So therefore, it's definitely greater than 1. And this is now your k plus 1 squared. So maybe you can just say that to summarize what we have done here, 2 to the k plus 1 is greater than k plus 1 squared. So by the generalized mathematical induction, we have now shown that 2 to the n is greater than n squared for each integer n which is greater than or equal to 5. That concludes our proof. For our next example, we want to show that for each natural number n, we have 2 raised to n plus 1 is greater than n squared. Now take note of the similarity of this with example 2. We have here 2 to the n is greater than n squared, but this is only true when n is greater than or equal to 5. So for our first method, you can actually use example 2. From example 2, 2 to the n plus 1 is definitely greater than 2 to the n. And example 2 says that 2 to the n is greater than n squared for n greater than or equal to 5. So therefore, it remains to show that this statement is true for the case n equals 1, 2, 3, and 4. Because example 2 starts with n is equal to 5. And this is easy enough to show. But what if you were just given this problem and I didn't give you example 2, which says that 2 to the n is greater than n squared? You really have to start with this one. So therefore, we will just use the principle of mathematical induction. So for our base case, n equals 1, 2 squared is greater than 1. This is not the formal proof. I will just give you the sketch of the proof. Then we proceed with our inductive step. Let k be greater than or equal to 1. What is it that we want to show? We want to show that p of k plus 1 is true. That is 2 to the k plus 2 is greater than k plus 1 squared. We write 2 to the k plus 2 as 2 times 2 to the k plus 1 so that we can make use of our inductive hypothesis. So again, we have 2k squared, which is equal to k squared plus k squared. Recall that we want to end up with this is greater than k squared plus 2k plus 1. So that is, we want to show that k squared is greater than 2k plus 1. This is what we want to show. However, this is not true when k is equal to 1 because you have 1 greater than 3, and when k is equal to 2, you have 2 squared greater than 5. How about when k is equal to 3? You have 9 greater than 7. So it seems that this is already true when k is greater than or equal to 3. However, our assumption here is that k is greater than or equal to 1. So how do we attack this dilemma? What you need to do is to treat the cases p of 1 and p of 2 separately. And then for the rest, p of 3, p of 4, and so on, you will now use the generalized mathematical induction here. So for p of 1, p of 2, treat them separately. Show that when n is equal to 1, that is true. When n is equal to 2, that is also true. For the generalized mathematical induction, your base case is p of 3, correct? And then for the inductive step, you will now have let k be greater than or equal to 3 here. And then we now write this as k squared plus k times k, but k is greater than or equal to 3, so that's greater than k squared plus 3k. And we now write it as k squared plus 2k plus k. And k is definitely greater than 1 because our assumption here is k is greater than or equal to 3. We just have to revise this part, show that it is true for n equals 1, n equals 2, and n equals 3. So for n equals 2, 2 cubed is definitely greater than 2 squared. And for n equals 3, 2 to the 4th is definitely greater than 3 cubed. So this is sort of your base case. You have to show that it is true for n equals 1, 2, and 3, and then proceed with your inductive step. So for our formal proof, we start with our base case. So I have here the base case for n equals 1, 2, and 3. And therefore, for our inductive step, let k be greater than or equal to 3. We now have the following inequality. So therefore, we have just shown that 2 to the n plus 1 is greater than n squared for each natural number n. For our next example, let us show that for every non-negative integer n, 3 divides 2 raised to 2n minus 1. Since our n here is a non-negative integer, our base case is at n equals 0. Since 3 divides 2 raised to 0 minus 1, that is 0, the statement is true when n is equal to 0. For our inductive step, let k be a non-negative integer, and we suppose that 3 divides 2 to the 2k minus 1. Hence, we have that 2 to the 2k minus 1 is equal to 3r for some integer r. We want to show that 3 divides 2 raised to 2 times quantity k plus 1 minus 1. Let us now consider this expression. This expression is equal to 2 raised to 2k plus 2 minus 1. How can we make use of this 1? what you can do is to separate your 2 raised to 2k because it appears here. So I will write it as 2 times 2k times 2 squared minus 1. From this equation, let's call it 1. This is equal to, my 2 to the 2k is 3r plus 1. And then I will copy 2 squared, which is 4 minus 1. And this is equal to 12r plus 3. And this is now 3 times 4r plus 1. So thus, 3 divides 2 raised to 2k plus 2 minus 1. Therefore, 3 divides 2 to the 2n minus 1 for all non-negative integer n. Here's another example. For every non-negative integer n, 9 divides 4 raised to 3n minus 1. For our base case, n equals 0, 9 divides 0. For our inductive step, suppose that we have a non-negative integer k, and let us assume that 9 divides 4 raised to 3k minus 1. Just like in the previous slide, 4 raised to 3k minus 1 is equal to 9r for some integer r. And we want to show that 9 divides 4 raised to 3 times quantity k plus 1 minus 1. We write this expression as 4 times 3k times 4 cubed. This is 3k plus 3 minus 1. And we make use of 4 to the 3k here. That is 9r plus 1. This is 4 raised to the 3k. It's equal to 9r plus 1. 4 cubed is 64. And then minus 1. This is now equal to 9 times 64r, and then I have 64 minus 1. That is 63, so plus 7. Therefore, 9 divides 4 raised to 3 quantity k plus 1 minus 1. And hence, this is true. For our last example, suppose that we have a fixed integer x. We want to show that for every integer n greater than or equal to 2, x raised to the n is even if and only if x is even. This is a biconditional statement, so therefore, we need to prove 2 directions. We prove this direction first. So that is, we are assuming that x is even. We will show that x to the n is even. Hence, x is equal to 2m for some integer m. We now consider x to the n. We show that it is even. We have here for every integer n. That's a universal quantifier. So we start with let n be greater than or equal to 2. Then we now show that x to the n is even. In order to do this, I will just write x to the n as x times x to the n minus 1 because I already know that x is equal to 2 times m. So this is 2m times x to the n minus 1. So thus, x to the n is even. For the other direction, we want to show that x to the n is even implies that x is even. This is where we use induction. So for our base case, we have that n is equal to 2. When n is equal to 2, that means x squared is even implies that x is even. From our previous video lecture, we have already shown that this is true. X squared is even implies that x is even. If you have already forgotten that, This can be easily proven by contrapositive. If x is odd, then x squared is odd. For our inductive step, let k be greater than or equal to 2, and suppose that x to the k is even implies that x is even. So we want to show that if x to the k plus 1 is even, then x is even. Since we want to prove this implication, we suppose that x to the k plus 1 is even, and then show that x is even. Since your x to the k plus 1 can be written as x times x to the k, then x is even or x to the k is even. Why is that true? Recall that if the product of two numbers is even, then at least one of them is even. This is what we have used here. If x is even, then we are done, because that is what we want to show. We want to show that x is even. If x to the k is even, then from our inductive hypothesis, x must be even. In both cases, we have shown that x must be even. Thus, we have just shown that x to the k plus 1 is even implies that x is even. Notice what I did here. Look at this one. X is even or x to the k is even. This is actually breaking it into two cases. Case 1, if x is even, and then case 2, x to the k is even. In both cases, we have shown that x is even. Just to conclude our proof, therefore, x to the n is even implies that x is even for all integers n greater than or equal to 2.